Oh my goodness, I should get started. Good afternoon, everybody. Welcome to another, I guess it's cloudy, not really rainy, a Monday afternoon with your host, me, Dr. White. Me, Dr. White. Almost forgot to do that. All right. As you know, I graded test number 3. Oops, it's broken. That's better. Test number 3. And I've sent back to you an email with all the points for each question. I'm going to go through the test in a little while. Let me remind you, let me check my glasses. Let me remind you, you should never, ever, ever be penalized for a mistake I make when grading. So keep an eye out. Look what you got after I've gone through the answers. Do not ask me during class. I always do that face to face too. Do you think I made a mistake? Send me an email or come to my office hour and I'll look at it. If I make a mistake, you shouldn't be penalized for it and I'll correct it. And I do. So, and I do that because last time I checked, I don't walk on water unless it's frozen. And even then, I stay off it. All right. Before we get into it, important announcement for this Wednesday. This Wednesday is International Chem 170 Turn on Your Webcam Day. So I'm going to ask everybody, if you don't turn it on, could you turn it on, please? Because it's International Chem 170 Turn on Your Webcam Day. But you didn't know that was a holiday, a special day in this. But with that, I better get to work. All right, first of all, I forgot to look at the average, but it was well above 90, I know. A couple of you got perfect scores, and all of you did really good. So thank you. Actually, you should thank yourself. I have something secret to tell you. You're learning organic chemistry, and you're doing it quite well. All right, let's get to work. Three. Now, if I were in your shoes, first of all, my feet would hurt because my feet are probably wider and bigger than yours. Uh, Anybody out there 4E with? See, I told you. But just in case, yeah, if I were when I was a student, I'd be wondering, what grade am I getting now? Now, what I'm about to explain how to figure out what grade you're getting right now in my class is based on the assumption you've handed in all the labs and you've done well. And if you've handed in all the labs, all of you who've handed in labs have been doing quite well on them, which is a good thing. And let's take a look at how to determine where you are. There are two methods you can use. Give me a second while I clean up some space here. And don't forget, if you have any questions about grading, email me or all right, thumbs up, people. Does everybody see method? I'll be real. I'll call it method A. Everybody see that? Am I being? All right, method A. Method A, take the sum of your 3 test scores, which you all have, add them up, and divide by 3, and you'll get a number X. If X is 90 and above, you're getting an A. If X is 80, 89, right now you're getting a B. There's still a lot of points left to go. So take a deep breath, relax. There's still at least 300 points left to go. Wow. But anyways, and if let me start again, and this is in my syllabus, 90 to 100 is, or 90 and greater, is an A. 80 89 B, 70 79 C, 60 69 C, and below the 60 is an F. Now, that's method A. Now, there's a method B. Am I creative with names or not? Not. But anyways, method B is, remember in my grading, the lowest test is drop. So for this method, take the sum of the two highest test scores, divide that by 2, and you'll get a number Y. And if Y is 90 and above, you're getting an A, 80 89 B, 70 79 C, 60 69 D, and below that F. And that's how you do it. And that's your standing. But let me tell you, there's still a lot more points to go. But overall, I'm very pleased. And more specifically, you should be very proud of what you're doing in my class. How many of you have heard organic chemistry is supposed to be real difficult and hard? It's not if you put in the time and practice, which I provide you the tools to do that. And guess what? You've been doing that. Thank you, and thank you. All right, any questions so far? I'll do anything except the meaning of life. I'm still trying to figure that one out myself. But, well, I just answered that question if you had it. Any questions? All right. Don't forget to hand in your labs. Sometime tomorrow, I'll post the lab we'll be doing this Wednesday, and I'll post your last week that you handed in labs. I haven't graded, I just haven't had a time to post it. Grading tests for online courses a lot more consuming time-wise than for a regular face-to-face course. Do I have a surprise for you today? You're gonna have, in a little while, Dr. White's show and tell. Did I tell you in grade school, teachers were afraid when we had show and tell because anything I brought in would scare them? Why? Because they had no idea what I was talking about. It was always something deep, either electronics or science. All right, let's get back to fats and oils. And let me just remind you something real quick. Remember, I've worked in this industry, so I'm teaching you stuff that's usually not in a book. And for tallow, yellow grease, and white grease, remember, this is beef fat, and you should know that. And both of these are different grades of pig's fat, which if you're cooking, you call that lard, but in the chemical industry, we never call it lard. And I have my way of designating that by showing this triglyceride, triester,
Excuse me.
yes.
Is this the beginning of the next lecture?
Yeah, lecturing right
topic?
now. Well, actually, Tom, go back and check. Last week I was talking about this and did a better part of chapter. I know you missed some of it, but good news, the YouTube videos are available to you. Okay.
So we're on chapter 15, lipids and detergents. Okay. And have you you did the page where
I've covered everything.
oh, you did the whole thing?
No, I'm up to the part where I'm about to talk about soaps and how soap works. So I'm just about done with a good part of it.
Okay.
But
Sorry to interrupt.
nothing to be sorry about. All questions are good questions in my class, always. And you should never, ever have to say you're sorry for asking a question in my class. And now let's get back to work. And remember, this is a designation. And just to remember, what's R sub F? It's from stearic acid. Which you should know the structure of. And this is what I mean by R sub S, because I have the carbonyl plus this. And the R sub O comes from oleic acid. And you should know the structure of oleic acid. Hint, hint, wink, wink, say no more. Have I done that this semester? That's from Monty Python, Flying Circus. If you haven't seen Monty Python, Flying Circus show, it was on in the 70s on Channel 11, and it's on YouTube skits. You should see it. It's one of the funniest things that's ever been on TV. And this is oleic acid. And at C9, that's how we write it. That's the beginning of your double bond. 1 plus 8, that makes that carbon 9. And this is oleic. And when I say R sub S, that's R sub O, I'm sorry. And you should know that. And to give a approximation of yellow grease, white grease, and tallow, this is what we have. And by the way, when I say R sub T, like in this molecule, what I'm really talking about here is this whole thing right there. The carbonyl carbon plus R sub S, the carbonyl carbon plus R sub O. And that's where the tallow comes from. It's funny, I've had students get grossed out. You mean my fabric softener comes from beef fat and pig's fat? And the answer is sure does. Does that mean things I see that have stearate or oleate in my makeup or my hand lotions comes from pig's fat or beef fat? Sure does, but it's so far removed. It's just a chemical. It's been purified many times over. There's few companies that use vegetable oils to do that, but it's a lot more expensive. Most don't. Now, one of the things I taught you, but since you might have been studying for the test and your mind elsewhere, is the following. Once in a while, review is good for your grade and learning things. Let me remind you, double bond, H2 and a catalyst. You break the pi bond, and each carbon double bond has a hydrogen. Now, carboxylic acids will not react with hydrogen and catalyst, but double bonds will. So what do you get? Two days later, I'll be finished. On a whiteboard, you have to wait too in a class. Now, if I consolidate this, notice this is CH2, this is CH2, 2 plus 7 plus 7 is 16. And this is what you get. And as I asked in class, but I'll ask again, what would be the product or products of that reaction? But first, let me back up. Hint, 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 big hint. Your turn. And don't forget, Wednesday is International Chem 170. Turn on your webcam day. So everybody, please be ready to turn on your webcam. And when you're done, give me a thumbs up. All right, I think everybody's done. Or they just want to show me your thumbs. Oh, that was an awful joke. Anyways, in here, what's our sub O? This. And what do we get? This, which is R sub S. So if I were to write this like this, you could write, and that would be, take oleic acid, hydrogenate it, you get stearic acid. And I'll let you try this one. If you take this molecule, react it with hydrogen and nickel, I could put down excess, but I'm a lazy organic chemist this afternoon, so I won't. What would be the product or products you get? Pro tip, esters are not hydrogenated. An ester will not react with hydrogen in a catalyst. Trust me, I've done this reaction on 40,000 pound batches, supervised it. They don't. And while you're doing that, let me do something on my own. All right, anybody? Well, I should say, thumbs up, people. Are you done? Show me your thumb. All right, I think everybody's done. What do we have here? Well, this ester won't react with hydrogen, but I have an R sub O, which has a double bond in it. And here's one too. Now, this R sub S. Is this a bunch of CH2, CH2? That won't react. Well, it's like you saw above, R sub O becomes R sub S. I'll still have my ester. Now this R sub S isn't going to react, so it's still R sub S. Now this R sub O, like you saw up here, becomes R sub S, and the same thing down here. And that's how you hydrogenate a fat and oil to make hydrogenated fats and oils. If I remember correctly, last week I told you about the story what happened to me when I was at that managers meeting, and the guy who was in charge of the rollout of I can't believe it's butter for the first time, and the problem he had. But those were hydrogenated fats and oils that they put some yellow coloring, some flavor, some water, mix it up, and it's nice and thick, and it tastes just like butter, and we can charge you a lot more money. So we make a big profit. Okay. Tom, just when I ask thumbs up, you don't have to put your thumb up. All right. All right, now let's get into something exciting. How does soap work? It's time for me to teach you how to get clean. Bet you never thought I'd cover that in organic chemistry. Well, that's organic chemistry too. Remember how I say organic chemistry is all around you, or I said, I'm going to teach you about my world of organic chemistry is your world of organic chemistry. You don't know, really don't know about that yet, but you are. So let's talk about how does soap work. And today is show and tell. A bar dial soap, that's my favorite. By the way, liquid soap is similar. So how do you get yourself clean? Your hands are dirty. What do? Water won't get the dirt off it. Use soap and water. Or your clothes is dirty. What do you use? A detergent. And that gets the dirt off it. Or your dishes are dirty. What do you use? A dishwashing soap. They all work the same way, including if you're washing your beard, which I do, and my hair, or anything you wash. This is how it happens. Now, when we talk about how soap works, and by the way, Am I being subtle enough? All right. When we talk about certain class of molecules, they're called surface active agents. These are molecules that interact at the surfaces between two things, like dirt, your skin, and water. And surface active agents, organic chemists are lazy, have been shortened to the word surfactants. And surfactants are special types of molecules. And Dr. White's an expert in surfactants. 2 of the 3 companies I work for, actually 3 of the 4, made surfactants. So does Dr. White know about this? Yes. Now, soap, and by the way, you should know what I'm going to be teaching you the next couple of slides. First of all, soap has what's called the hydrocarbon tail, also known as lipophilic. Phil means loving, lipo, fat. It also has a polar head, which is hydrophilic. And I'll never ask you what's lipo or hydrophilic, but philic means loving, hydro, water, loving, or polar. Now, remember, like dissolves like. Well, I'm going to have to teach you some things right now about that. Oh, wait. Dr. White's going to do the first thing I've done all semester. It's time for a cliffhanger. You've got to hang in there until we come back from our break to find out how soap works and what's like dissolves like. Will he come back and tell you about that? That's the cliffhanger. I will. I'll see you in 5 minutes. Come back at 1:55. I'm going to get up and stretch. I love that. Time to get back to work, everyone. Come out wherever you are. I haven't thought of that in a long time. How many of you, when you were young, played hide and seek? What was it? Oli, 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 home free, free? Something like that. Wow, that goes back too long. All right. Welcome back, everybody. It's time for Dr. White to teach you how to get clean. Now, if I had a dial that only went up to 10, I've just turned it up to 100. One of the most important things I'd like you to go away from my class this semester is to learn how soap works, because you use that in your everyday, or at least I hope you do, for either cleaning your hands, yourself, your clothes, your dishes, your car, your floor, whatever. How does soap work? Let's get back to what we were talking about. And soap, what's the structure of soap? I'm going to show you it. It's got a hydrocarbon tail and a polar head. And remember, like dissolves like. All right, let's go. Thumbs up, people. Do you see my whiteboard? Thank you. The following you should know. I better make it real obvious. First of all, you should know the structure of soap. One way is this way. Non-polar tail and a polar, something with a charge on it, head. Now, why am I talking about this with fats and oils? Well, it turns out the oldest soap, which is still being used, like in that bar of dial soap I showed you, is this. This carboxylate anion, where R here is R sub T, meaning this has, with the carbonyl carbon, R sub T, 16 to 18 carbons. This is my nonpolar tail. And this whole thing right here, because it's got a charge on it, is my polar head. And just to show you something interesting, everybody see soap on your screen now and the ingredients? I looked up ingredients of, if I spell it right, ingredients of dial soap, which is what I have right here. If you look at sodium tallowate, sodium tallowate is the carboxylate anion of a mixture of stearic and oleic acid and other carboxylate anions of the carboxylic acids that make up the esters in, guess what? Beef fat and yellow grease and white grease. So the soap, this one, and notice sodium cocoate, palm kernelate are smaller chains. It's got water, why it has talc, and the coconut oil, palm kernel oil, and tallow acid is just, if anything hasn't been made into the carboxylate. It's got glycerin, peg methyl, Let's see something. Ah, here it is. No, they don't show anything. PEG methyl is if you take methanol and react it with uh, 6 moles of ethylene oxide. I taught you that. That's in there too. And there's also a couple others. One is titanium dioxide, and that's what makes it white. But anyways, the important thing is the carboxylate anions. Now, there's a very important concept that I have to teach you, and that's Lye dissolves Lye. And you should know this. We're still under hint, know this, big letters know this. And what's Lye dissolves Lye? I guess I should have written substances. Polar things are soluble and other polar things are substances, and nonpolar things, substances, are soluble in nonpolar substances or things. And this is Lye dissolves Lye. It's a rule of thumb, meaning about 98% of the time it's true. There are exceptions, otherwise we call it a law. Now, you should know polar. The most polar thing, water. Alcohols are polar, and salts like sodium chloride are polar. What things are nonpolar that you should know? Well, vegetable oil is nonpolar. Baby oil, which are hydrocarbons, is nonpolar. And Vaseline, which is more hydrocarbons. Gasoline is nonpolar. And two most important things, dirt is nonpolar. Yes, dirt has been characterized, and also grease. These are all nonpolar. If you mix oil and vegetable oil together, they're not miscible or soluble. And how many of you have ever seen oil vinaigrette dressing? The oil is vegetable oil or other oils, and the vinaigrette is essentially acetic acid and water. So that's why they don't mix. Now, interesting thing, a number of years ago, I teach this in my Chem 112 class when I taught it, and a student who was quite sharp said, well, if that's true, is Vaseline soluble in vegetable oil? I said, I don't know, I've never tried it. Next lab we have, when we get into the lab, I'll give you a beaker, I'll give you some vegetable oil, some Vaseline, mix them together and see what happens. And the answer is they are. So Lye dissolves Lye. Now, how does that help us? All right, I just turned the switch up to 5,000. Let's look at a magnified piece of dirt that happens to be on my hand. If there was dirt, I washed my hands, but if there was, and this is non-polar. If I have water and I'm trying to get the dirt off my hands, water looks at dirt and says, you're non-polar, I'm polar, I know Lye dissolves Lye, you aren't coming with me. I'm not going to take you off your hands, dirt off your hands. So what do? Use soap. Now, soap has a nonpolar tail, which is attracted to the dirt. This is a soap molecule, and you should know this. But there are a lot more molecules than this one when you're washing your hands. And it totally surrounds the dirt molecule. And if you look at the slides, which I will, well, I'll give you time to copy that if you're copying it. And another way of looking at it is this fancy picture. Did everybody see the fancy picture on your screen now? This in the very center of this, each blue sphere, is a dirt particle. The lines coming out are the tails of soap, the nonpolar tail, otherwise known as lipophilic, nonpolar. And at the end of the soap molecule, these little blue with the negative, is the head of the soap molecule, and the sodium cations are floating around here. And notice here it says soap molecule, and this forms. Now they've cut off a segment so you can see inside, but this part right here, here, also has the soap molecules, so it's totally surrounding it. Now, there's a name for that when that forms, and you should know. When this forms, this is called a micelle. And you should know that dirt surrounded by soap, and here's the structure you should know, is a micelle. Now, because a micelle is formed with the polar heads on the outside, and now water looks at the micelle and says, oh, look, micelle, you're polar, I'm polar, let's go down the drain together. And they do. And that's how you get dirt and grease off your hands or anything else. You form micelles, and the micelles make the now dirt particle is now a micelle particle and makes it look polar to water. And water says, micelle, you're polar, I'm polar. Like dissolves like. Therefore, let's go down the drain together. I'll say it again. This is something you should know. Hint, hint, wink, wink, say no more. You should know. Soap structure, nonpolar tail, polar head. Like dissolves like. That means polar things are soluble in polar things, nonpolar things are soluble, nonpolar things, the two don't mix together. You should know. Polar. Water is the most polar substance in the universe. Alcohols are polar, salts are polar. What are nonpolar? Vegetable oil, baby oil, Vaseline, gasoline, dirt, and grease. When you're trying to get like a piece of dirt or grease off your hands, water won't do it because dirt is nonpolar, water is polar, and they know like dissolves like. How does soap work? Soap is a surfactant and interacts with the dirt. The nonpolar tail is attracted to dirt, which is nonpolar, and that forms a micelle, and the outside polar heads stay far away from the dirt and form a micelle, and the water looks at the micelle and says, oh, micelle, you're polar, I'm polar, you're soluble in me. Let's go down the drain together. And they do. And that's how you get clean. Now, a couple interesting things. couple of years ago, I was watching TV, and don't forget, Dr. White's worked in this industry heavily for many decades. I have patents in this industry. I'm watching a TV commercial. This happened a number of years ago. And they said, and our product is so good, it even cleans greasy dirt. I almost fell off my chair laughing. Greasy dirt or dirty grease? Well, come on, give me a break. But anyways, you hear a lot of strange things in commercials that are, make you wonder who wrote them, not a scientist. But then again, they're designed to entice you to buy the product, not to teach you science. Now, how many of you have heard of the product, which I've been told is a very good product, called micellar water? Guess what? There are no micelles in there. It's when you put it on your face, you're forming micelles, wherever else you use to clean it. And the first time a student in Chem 170 a couple of years ago, you just taught us about micelles. And she brought me in one of her magazines and showed me an ad for micellar water. And guess what? There's no micelles in there. Because they'd put in a handful of dirt, which they don't. Everybody see on the screen? It's got glycerin, other glycerin, and this right here is preservative and the surfactant cleaning. Notice this disodium cocoa amphidiacetate, that's your soap. And what all these together is nice for your skin, and it cleans your face. And I'm not saying there's anything wrong with this. I'm just saying when you buy the product, like here, Garner Skin Active Micellar Cleansing Water. There's no micelles in there. It's only when you put it on your face or whatever, you form micelles. Now, I've been told and mainly women use this for makeup and other aspects of cleaning, that it works quite well, which is good. But anyways, that's that. Now, are you ready for not one, but two? Show and tell. How many are familiar with liquid soap? If you look at the back, you'll see sodium lauryl sulfate and sodium laureth sulfate. What are those? This I'm not going to ask you to learn, but I figure I'd teach you anyways. No, I was right the first place. I'm debating how to draw this, but this is sodium laureth and sodium laureth and laurel. I always forget which one's the laurel and which one's the laureth. And essentially, you have an R group, which is about 9 to 12 carbons, benzene ring, CH2OH, CH2CH2O, and then a sulfate ester. So here's my nonpolar tail, and here's my polar head. And same thing down here. And this is the liquid soap. It's different than, know something nice where I've gotten, Dr. White just had a major brain freeze. This is the first time this semester that's really happened. All right, let's do this again. I'll never ask this on a test. Sorry about that. And this is usually about C12 and other isomers. And here N is from 3 to 5. Here, you both have your nonpolar tail. And here you have your polar head. And if you take an alcohol, react it with ethylene oxide, here it's 1 mole, here it's 3 to 5 moles, you'll have a polyether alcohol, and then you can make what's called a sulfate ester that you can form into sulfonate anion. And that's how they make it. By the way, this R group comes from either vegetable oil or animal fats too. And it's more liquid, and people like that more. All right, but both is they form a micelle because like dissolves like, and you should know that. All right, and I was probably one of the few people in Northern Illinois when I was taking my shower today. I'm going like this. I'm saying, oh, I'm making micelles. And I did. But then I'm an organic chemist. And next time you wash your hands, think about it. You're doing organic chemistry. Not only is how this got made as organic chemistry, but how it interacts with the dirt on your hands or wherever else you're cleaning, and removes it because like dissolves like. And I talked about synthetic soaps and detergents, seaboard. Here's where I got confused. This you do not have to know. I'll never put this on a test. Most of your laundry detergents are linear alkyl sulfonates. And they put other things in there to make it work better. I'm a longtime user of all Tide. They all use these linear alkyl sulfonates. Think of a benzene ring. You know how to put an R group on there, fructose alkylation. You can sulfonate it with sulfuric and nitric acid. No, sulfuric acid and sulfur trioxide. And then you make the the sulfate anion by reacting with base, and all your laundry detergents about. There are a few new ones that are based on other things, but 99% of your laundry detergents, this is the molecule that does the cleaning. And if you notice right here, by the way, this is C9 to 12. Here's my nonpolar tail. And here is my polar head. And that's how it works. And this also forms micelles. And once you form a micelle with the dirt or grease, whatever's on your clothes, the water looks at the micelle and says, oh, micelle, you're polar, I'm polar. I know like dissolves like, let's go down the drain together. And they do.
I have a question.
I do questions.
200 years ago or before that, people would, use a rock and and some lard, to wash their clothes.
Nope. You're close, but no
Okay.
cigar. I don't smoke cigars, but anyways, I tried it once. I used to smoke a pipe and I was heavily into cigarettes, but I gave that up decades ago. But let's take a look at what you're doing. That's a good question. First of all, show of hands, how many of you have ever heard of Lye Soap? Well, lye is sodium hydroxide. And you know how the settlers and for many eons made their soap? Sodium hydroxide's old name was lye. And you take sodium hydroxide and water, you do a saponification. Remember the structure here. And thank you for asking me about that, Tom. Sodium hydroxide, water. This is an ester. I get these alcohols. We've done this in class, which is why I'm doing this quicker now. You get glycerin, which you can separate out, and you get this white solid that you can take out once the liquid, whatever you're heating it in, because you usually boil it to make it go quicker, is a mixture of these two carboxylate anions, mainly. And what do we call this mixture? Sodium tallowate, which you saw is they're still using to this day in my bar soap. And that's what the settlers did. Now, there's a theory. How did this first get discovered? Well, the theory is, and it's a conjecture more than a theory, eons ago, people would cook big pieces of meat over a fire and, turning it, long ago. And what happened to the fat? It would drip down into the wood. Now, when you burn wood, what's there a lot of there? Well, some moisture, but potassium hydroxide. And that formed it into soap. And that's the conjecture how people first figured out. And then later on, chemists came along, found out, or settlers used lye. And lye is the sodium hydroxide, and that's how you make the soap. So, Tom, does that answer your question? And you still use the rock to pound on. Have you ever seen the old washboards, from the
Right.
1800s? Same thing, except
Well, I know when we go camping as a family, We would get a bar of Fell's Naphtha soap. It looks like, Scandinavian goat cheese.
No, I've
And we
never
would
had
use that
All
and
right.
keep that in our.
Do you bring your own rocks or what?
No, we would always search for those. We'd give the kids a nickel a rock.
Ooh, I'm gonna have to come camping with you. Make a lot of money. See me come to your campsite with a pickup truck full of about a couple 100,000 rocks. All right, pay up. But that's soap. Soap's been around and it's organic chemistry. All right. Now, next part, I'm turning the switch off totally. Will this be on a test? But I thought I'd talk about something interesting. It turns out there's a triester that's very important to our body called phosphoacylglycerides, also known as phospholipids. And these are esters of glycerin, but you also have a third ester from phosphoric acid and triaminoethanol. And it looks like this. Let's do something. Instead of me making a everybody see on your screen the fancy little structure there? If you look here, these lines just tell you stereochemistry, but this carbon is bonded to this one. And this is the backbone of a fat or oil. Here's our groups, our ester to the CH2, CH. And the third ester is not another carbonyl group. It's an oxygen formed to come on. Let me do this. There. This is phosphoric acid reacting with this. And this has got a negative charge, a positive charge here, net zero charge. But this is your polar head. This is your nonpolar tail. And these are acyl phospholipids or phospholipids. Now, where do you find phospholipids? They're found in egg yolks and soybeans. Now, used to make mayonnaise, I'll go through this in a second. Now, one thing I will tell you, a personal thing, phospholipids have an amazing effect on your body, at least mine personally. And I get mine from soybeans. I like the shelled edamame. You can get it at my local supermarkets, and I buy a lot and use a lot. You boil them and then you freeze them, and there's sort of no taste. You put other stuff that tastes them. Now, every once in a while, I stop eating my soybeans, and I don't sleep as well, and I don't think as well. When I go back to eating on a regular basis soybeans, and works much better for me personally with the edamame soybeans as opposed to something like tofu, which is made from soybeans. I sleep much better, and my mind is much crisper. Better watch out when Dr. White's got a crisp mind. It's stinks. No. But anyways, and it's just my personal thing. Will it work for you? Don't know. But let's talk about how many of you are familiar with mayonnaise? That's a product you can buy or make yourself. Now, how do you make it yourself? Mayonnaise is an egg, water, and vegetable oil. But wait a second, Dr. White. You told me lye dissolves lye. And let me just check. Thumbs up, people. You see mayonnaise on your screen? Thank you. Oh, by the way, the best is Hellman's, my personal opinion. But you have water and vegetable oil. And the two won't mix. But in mayonnaise, they do. Why? Because you use an egg. And what does an egg have in it? The phospholipid, which is a surfactant. And what happens is you mix it together and it forms a colloidal dispersion. That's what you see in mayonnaise, because the surfactant in here, the phospholipid in the egg yolk, helps bring water and vegetable oil and keep it together. If you've ever seen someone who hasn't made mayonnaise quite correct, with time it will separate too, which you don't want to. Now, have you ever wondered why a egg yolk is yellow? It's yellow because phospholipid is yellow. I did some experiments years ago with phospholipids that was industrial grade, and I got a bottle from the supplier and it was yellow. And it dawned on me, that's why egg yolks are yellow. All right, let's talk about steroids. But before we do, let's go way, way back to the beginning of this chapter. I talked about lipids. I talked about two types of lipids. One is saponifiable. That means can be hydrolyzed under alkaline or base conditions to yield salts and fatty acid, plus now you know also glycerin. And these are fats and oils. Now, what are non-saponifiable lipids? Those are things from plants and animals that are not soluble in water, and also do not undergo hydrolysis under base conditions. We have another name for those in our body. Don't get dizzy. And those are known as the steroids. And these are non-saponifiable lipids. Now, all steroids have this four ring system, A, B, C, and D. And you should know how to draw this. And if I ask on a test, draw the steroid ring skeleton, you should know. Let me show you how to do this. You have a 6-membered ring. Then fused or sharing right next to it is a 6-membered ring. Then at 12 o'clock, you have another 6-membered ring. And then next door, you have a 5-membered ring. 6, 6, and it has to be up here, 6 and 5. And this is the steroid ring system. For those who don't know, now I'm well beyond my knowledge of the human body and biochemistry and biology, the steroids are also known as your hormones. But you should know how to draw a steroid ring system. Now, when I was in grad school, the research group I belonged to with Dr. Roosh, who I will forever, ever, ever be grateful because he really trained me and taught me how to be a true organic chemist and synthetic organic chemist. Half the group worked with steroids and the other half group with sesquiterpenes, molecules that I worked with, this bicyclic ring system. I worked with these types of molecules. This is one I work with. How to make it and how to react it. And they're a little, but both were complex and both dealt with carbonyl compounds. Now, there are times I get into stuff that has nothing to do, it has everything to do with chemistry, organic chemistry, but no way am I taking a moralistic pro or con I'm just teaching you the organic chemistry, and this is one of them. Give me about a minute or two, because I got to do something on the internet. Hang in there, almost done. So ever got a question? Hang in there. Let's see what your question is. Oh, you're welcome, Tom. All right. Everybody see testosterone on your screen? All right. Now, you guys know organic chemistry, so I can talk to you. This is the structure of testosterone. You do not have to write it down. These wedges are methyl groups. Every end of the line, and it's showing stereochemistry, meaning it's coming towards you. The hydrogens with the dash are going away. But if you look at this, we have our 4-ring system. Over here, I have a ketone, double bond, alcohol. This is testosterone. This is responsible for things like the beard I have or other things. This is a male hormone, or otherwise known as a steroid. Now, let's look at a female hormone. And this is progesterone. Everybody see it on your screen? And this has the same 4-membered ring as a carbonyl ketone here, double bond, the A ring. But in the D ring up here, instead of an alcohol, we have a ketone. So this is progesterone, one of the female hormones. Now let's go back and look. Testosterone, alcohol up here, progesterone, ketone up here. Doesn't that explain the difference between men and women? Men are alcohols and women are ketones. But you never thought of it that way, and probably won't again. But now you know I'm a synthetic organic chemist. Now, let's talk about something very important, and that's the woman's monthly cycle. How is that controlled? By a key hormone or steroid. And that key hormone or steroid is this one right here, estradiol. Notice you have, does everybody see estradiol on your screen? Thank you. You have a 4-4-4-5 member ring. It has that ring skeleton. Now notice here it's different. The first ring has a benzene ring with a hydroxyl group on it. This is an aromatic alcohol. Then over here you have an alcohol. And this, based on the level in a woman's body, and now Dr. White's well beyond the level of his expertise of human anatomy, but this controls her monthly cycle. Now, organic chemists found that another molecule This is quite expensive to come by, very expensive. But another molecule that you could make from cheap plant materials, a woman's body was confused and it thought it was really estradiol. And that other molecule is this one right here, ethynyl estradiol. Instead of an alcohol, up here the A ring is the same, B, C, but up here, instead of just having a alcohol, you have a triple bond. And this is similar to Grignard attacking a ketone. And that's how they make it. And this is ethynyl estradiol. And this is a key active ingredient in birth control pills. Because it can be made cheaply, inexpensively, back in the 50s and 60s, organic chemists and actually pharmaceutical companies started making birth control pills. And think about it, birth control pills, if they cost $100 a piece, how many women would be taking them? Not many, but they're not that expensive, or at least they're affordable. And this has changed our world because now a woman, if she wished to, again, I'm taking no moralistic, whether you're for or against birth control, but if a woman wanted to, could control her body and not get pregnant when she didn't want to get pregnant. And therefore, this has had a major impact on our world. And that's because of organic chemistry. They were able to convert a cheap steroid from plants using organic chemistry into molecules similar to estradiol, the hormone in a woman's body. And how does the birth control pills work? It has different levels of this molecule. And if a woman gets pregnant, it keeps it at a level that won't allow the pregnancy to continue. Now I'm well beyond my level of medicine. But anyways, this is the chemistry involved, quite important chemistry, because it affects many, many women on our planet. And that's our chapter on lipids and hormones and steroids. And remember, the next time you wash your hands, don't forget, you're making my cells, not my cells, you're my cells. Oh, that was an awful joke. Oh, Dr. White can knock them out anytime. Awful jokes, that is. And I'm not even charging you extra. All right. Do you know what time it is? It's new chapter and functional, or not functional, new chapter time. And I better warn you, this new chapter is very dangerous. It's fattening. It's real dangerous. It will get you cavities if you're not careful and put on weight. And what are we going to talk about? Carbohydrates. You know, the three major food groups. We've done fats and oils. We'll do carbohydrates, and later on we'll do proteins, even though you know there are four major: alcohol, beer, or pizza, potato chips, and I forgot the fourth one. Salami sticks in my book. But anyways, all right. First, a disclaimer from Dr. White, and that is this chapter, we're going to be talking about carbohydrates, which, if you're reading the book, is chapter 18 and part of chapter 5, which I skipped. And we're going to talk about, in this slide, you do not have to write down anything from it. We're going to talk about things in biochemistry, And biochemistry really is the study of chemical substances found in living things and their chemical interactions with other things. Now, for some reasons, people think you're doing biochemistry and all of a sudden, pookie, we're doing magic. No, you're still doing organic chemistry. It's just in your body or a plant or something that's alive. And the functional group chemistry that you've learned for organic molecules occurs just the same way in bioorganic molecules. In other words, functional group chemistry going on in your body is the same as what we studied, which makes it exciting. And I won't ask you, but a biochemical substance is really a chemical substance like a ketone aldehyde or whatever found in something that's alive, but it doesn't make it any different than if it's outside. All right, switches on. Let's talk about carbohydrates. You should know, what is a carbohydrate? The carbohydrate is a polyhydroxyl aldehyde, polyhydroxyl ketone, or compounds that yield such polyhydroxyl aldehydes or polyhydroxyl ketones upon hydrolysis. That means reaction with water. Now, what's the word poly mean? Many. Hydroxyl OH. That means you've got a molecule that has an aldehyde and a many hydroxyl groups. Polyhydroxyl ketone is a ketone that also has lots of OH groups. Now, I will never ask you to learn the structure of fructose or glucose. Now, this is called the Fisher projection, and I'll teach you later on what that means, but each intersection of a line, here, here, and here, is a carbon atom. So here we also have a carbon atom, and same thing here, here, here. And notice I have my software for glucose writes an aldehyde, not like this, but like this, which if you go back and look at my slides, I said some people write aldehydes. So this has an aldehyde. And this right here, R group carbonyl, R prime, this is a ketone. And therefore glucose, which I'll teach you about, is a polyhydroxyl aldehyde. And fructose, which I'll teach you about, is a polyhydroxyl ketone. These are both carbohydrates. Now, normally in our society, when you're talking about your diet, which I got to watch my carbs, you're talking about longer things we call starches. And I'll teach you, those are carbohydrates too. But the true chemical definition of a carbohydrate includes more than just starches. Now, if you're a carbohydrate chemist, which I'm not, even though I do consume carbohydrates, well, I like them too much. But anyways, switches off for the following definitions. You have a monosaccharide. And those are carbohydrates that contain a single polyhydroxyl aldehyde or ketone. So if we come back here, glucose and fructose are monosaccharides. This I'll never ask you on a test, but your other classes, especially if you're doing anything with food or dietitians or whatever, we'll talk about these. So I want to cover these definitions. So a monosaccharide is a carbohydrate that contains a single polyhydroxyl aldehyde or ketone. Oh no. Time flies when you're having fun with soap and steroids. It's time for a break. I'll see you in 5. Come back. Oh, I actually went a little longer than I should have. Come back at 2:55. I'll still let you out on time today. I'll be right back. Sorry about the late start. I'll go an extra 5 out. No. Time to start. All right, thumbs up, people. You see carbohydrate classification on your screen? Now, do you see it on your screen? Thank you. Don't scare me like that. All right. Now, we're talking about monosaccharides, and those are carbohydrates that contain a single polyhydroxyaldehyde and ketone. Remember, switch is off right now. Now, you can link together like a polymer, and I'll teach you that later this chapter, monosaccharides like fructose and glucose and other ones. You can link these together or these together each other or these, not that much these. And you can make what's called, and I don't even know if I pronounced this right, oligosaccharide. Those are carbohydrates that contain from 2 to 10 monosaccharide units. Again, switch is off right now. Now, why do carbohydrate chemists have to have all these fancy names? Don't know. I'm not a carbohydrate chemist, but they do. So I'm introducing you to them. Now, there's one oligosaccharide I do want you to know, and that is a disaccharide. You know, dimethyl, 2 methyl groups. Disaccharides are carbohydrates that contain 2 monosaccharides that are covalently bonded to each other. Now, I won't ask you what is a disaccharide, but the most important disaccharide you should know is sucrose. And you should know sucrose is table sugar. If I ask you what's the common name for table sugar, it's sucrose. And you should know that. Hint, double hint, big hint. I'll never ask you what is a disaccharide, but I'll expect you to know that table sugar has a name, sucrose, and it is a disaccharide. And I'll teach you later on, sucrose is really a glucose and fructose molecule bonded together. Isn't this getting exciting? We're getting into the sweet stuff of organic chemistry. Oh my goodness, I just did a good joke. For those who are into cooking, we're getting deep into stuff in cooking. Now, you can also have what's known as polysaccharides. Again, switches off. And polysaccharides, poly means many. You learned that in polymers. And many saccharides. These are carbohydrates made up of more than 10 monosaccharide units bonded together. And the most common polysaccharides you're familiar with are starches. Starches are polysaccharides. And Dr. White loves his starches. Oh my goodness. Look out. There's nothing better than the rotini with some butter and garlic butter on it and a little good cheese on there too. I'll let you pick your favorite cheese. Romano would be my choice. I'm getting hungry already. See how dangerous it is being in my class? All right. Time to slam on the brakes, and we're going to switch to another chapter, and that's chapter 5. Now, some people teach this before we get into carbohydrates, but since you're not going to use it until carbohydrates, I don't do it earlier, I do it now. And I'm going to teach you in this part of the chapter 5, the chemical difference between your right and left hands. Yes, I will. You really? Yep. And this is important. This is an important part of organic chemistry, and plays a real important role in carbohydrates. All right, switches on. This chapter deals with chirality. And when we talk about chirality, you should know chiral is the Greek word for handedness. And about 3 summers ago, I actually had 2 students in my class at the same time that were both fluent in the Greek language. And they said, yes, chiral means handedness. And what do we mean by handedness? Carbohydrates exist in 2 forms, like your right and left hand. If you notice there, I have my right and left hand. They look similar, but they're different. And I'll be teaching you how they're different this chapter. But you didn't think I'd get into your hands, and we'll also talk about your feet too. Now, when we talk about chirality, remember, you should know chirality, chiral, Greek for handedness, like your right and left hand. I have to teach you some things. I'm going to assume everybody in our class has looked in a mirror or has access to a mirror somewhere. If we were still face to face, I could say you could go into, at least the men's restroom have mirrors at ECC. I'm going to assume the women's do too. I've never been there, never will. But for those of you who have been in the women's restroom, I assume they have mirrors in there. And in your homes, I'm sure everybody has a mirror in there. Now, there's 2 types of mirror images. One is called superimposable, and the other is non-superimposable. I'll never ask you what is the definition of a superimposable or non-superimposable image, but you should know what it means, because you'll see in a while, you'll have to know the operational definition. Superimposable, that's an image that coincides with all points when images are laid upon each other. In other words, if I have, trying to look for something real quick. All right, hold on. I have a very important warning to tell you. This part, Dr. White's going to do some artwork, and make sure you don't fall off your chair laughing your brains out and hurt yourself. Hold on when you're laughing that hard. I'll never be an artist. My mother was good. Let's look at what we mean. First of all, I think you've all taken and looked in a mirror. You have your image and you have the reflection, your mirror image. Now, hold on. Here it goes. What is this? A sewing needle. The pointy end part, you put the thread in. Yes, you can laugh now. And if I were to hold a sewing needle up to a mirror, guess what I'd see? The reflection. If I were to pick this up and lay it over there, every point or every part of it would superimpose on the other. Here I have a red rubber ball. Plain rubber ball. Those of you know the song, bouncing back like a rubber ball. Never mind. But anyways, if I pick the image up, I can superimpose it on there. Yeah, ooh, I got something I can do. Look out. Great moments in teaching organic chemistry. This is a model. In the center is a carbon atom, and coming out are my 4 bonds. Remember, carbon has, oops, fingers broken again, 4 bonds to carbon. And if this were methane, I have hydrogens here. Oh, I've got another one. And if I hold it like this, here's my methane, here's my mirror image, and notice they're superimposable on each other. The silver goes silver, black, 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 black. This, or my models are mirror images. If I had a mirror right between here, like if you looked here, you'd see this. Hold on. It's easier in a classroom. You'd see this mirror image if my hand got out of the way. And so these are mirror images. If I had a mirror in between them, and they're superimposable. That's one type of mirror image. And there are two types. The other is non-superimposable. That means they're mirror images where not all points coincide when the images are laid upon each other. Now I'm going to teach you something real neat and you can impress your friends, neighbors, and loved ones with. I have a homework assignment for you. What? Yeah, I do. I'm going to assume all of you have access to a mirror. Stand in front of the mirror, or you can sit if you have that kind of mirror. Hold your right hand up there. And what are you going to see in the reflection? Your left hand. And your hands are mirror images. But are they superimposable? Let's find out. Oh, no, they're not. If I line up my thumbs, the rest of the fingers don't line up. Line up my center finger, my pinky and thumbs and everything else don't. If I do my index finger, nothing else lines up. Your hands are mirror images, but they're non-superimposable. So your hands are non-superimposable mirror image. Oh, by the way, I can't resist. Everybody know what this is? Spider doing push-ups on a mirror. Now, true story, I got to tell you about this. This is really funny. I think it was my first or second year teaching this, and students were having a hard time mastering this. So one of them pointed out, you know, you spelled superimposable wrong and non-superimposable. I had superimpossible and non-superimpossible, which is why they were having a hard time, because it was superimpossible. True story. Once I changed it to superimposable, things were better. That's really a true story. I don't know any fake stories. All right, now, when it comes to chirality, hint, switches on big time. Speaking about, first of all, there are two types of objects. One is a chiral object and the other is an achiral. I'll never ask on a test, define chiral or achiral object, but you should know how to identify objects as chiral or achiral. Now, chiral object, that means it has handedness, is an object that is not identical to its mirror image. A chiral object has a non-superimposable mirror image. Achiral, A is the prefix meaning without. Achiral doesn't have handedness, is an object that has a superimposable mirror image. It's identical to its mirror image. So chiral object, non-superimposable mirror image, excuse me, achiral, superimposable. Remember, A means without, which reminds me of a story. Oh, I got time. Yes, I do. When I was a postdoctoral fellow at the University of Illinois Chicago Circle, I was working for, he was a great chemist, organic chemist, and you become a postdoctoral fellow after you've gotten your PhD and you got to move on, but you don't have a real big job. So you work for another professor till you get a real job. And you're pleasantly poor. You get a nice salary, not that great. and you get to learn things. And this instructor, professor, taught me a lot of organic chemistry, and his name was Professor Moriarty, yes, just like in Sherlock Holmes. But anyways, uh, Professor Moriarty, and I don't know if he's still alive or not, but anyways, uh, he's the only person I've ever met in my life that was amoral, not immoral, amoral. He just had no moral compass whatsoever, which means he could be very dangerous. And there are other Dr. Moriarty stories, but I'm not going to tell them. But he taught me a lot of good organic chemistry. And one of the things he taught me was, unlike most academic chemists who spend years on a problem, Moriarty was like a hawk. He'd swoop down on something, and if he couldn't come up with something in 6 months to years, that I'm leaving this, I'm not going to waste the next year or two and find out it still won't work. And that was a very important lesson I learned about research that helped me in industry, which is you either get it done quickly or you move on. So we have two types of objects, chiral object, achiral object. And now let's have some fun. And let's do a couple. And let's look at A. Is A round snowball, perfectly round, a chiral or achiral object? And how do you do that? Well, you've got to consider the mirror image. Oh, by the way, I could use this one. You have a snowball. Here's this mirror image, and it will be totally superimposable. And therefore, it would be achiral because it has a superimposable mirror image. Now, unfortunately, and I'm not going to stand up and stick my feet in front of my webcam, but in a classroom setting, I could direct you down. Is your left foot chiral or achiral? Well, how do you do that? Well, try this in the comfort of your home. Take off your socks or whatever. You have your left foot and your right foot, they're mirror images, but they're non-superimposable. Because let's assume my hands were my feet, even though they're not. Got your big toes, they'll line up and the rest don't. Your little toes, this little one toe, whatever, anyways, won't line up with the rest of the toes. And your toes, your feet are non-superimposable mirror images. And that makes them chiral. So your foot is chiral. Now, anytime, this is a big secret, but anytime you see left or right in a description, that immediately tells you, like your hands, it's chiral. So if I were to say, is my right winter glove chiral or achiral? And immediately you know it's chiral. Now, let's think about something, then this won't be on a test. How many of you have ever played the game Simon Says when you're young? You know, Simon says this, I think you all have. Well, let's play Dr. White says. Dr. White says, touch your right cheek. Go ahead. Dr. White says, take your hand off your right cheek. Now, is your face chiral or achiral? Ooh. Think about it. You know the difference between your right and left cheek. If I said touch your left cheek, it wouldn't have been the one you just touched. That means your face is chiral. But you never thought about that. You can impress your friends, neighbors, and loved ones next time. Now, let's do a couple more, and I'm going to let you have some fun. Have some fun. Which of the following are chiral or achiral? Chiral, non-superimposable mirror image. Achiral, superimposable mirror image. And just in case you can't read my handwriting, C is a tube sock with no toes. You know how they have, women's have the socks with the toes in them. These don't, or any writing on them. Your pants, the kind with a zipper and button in front. A mitten with no leather palm, and a four-door car. Have fun. Which of these are chiral? Which of these are achiral? And when you're done, give me a thumbs up. And do it again for those people who are on the screen now. If you're done, give me a thumbs up. All right, it looks like everybody's done. Let's go through this. Now, remember, don't fall off your chair laughing. All right, let's do a tube sock. And I would do this on the board, and here, I have a tube sock. No toes. Here's its mirror image. The other tube sock or its mirror image. And guess what? This is superimposable. If I rotate it, it will superimpose. And the other way of thinking about it is, if you have tube socks, does it only fit on your right or left foot? No, you can wear them on both. Therefore, your tube sock has a superimposable mirror image, and therefore, this is achiral without chirality, handedness. Now, this is a tough one. Now, your pants with a zipper in front and maybe pockets in the back. No, I'm not going to do a drawing of that. But think about it. If you have a pair of pants with a zipper on front, and if I were to ask you, touch your left pant leg, you could. Touch your right pant leg, you could. Now, think about this, and this is something I usually tell in class. If you put your pants on backwards, put your right leg in your left pant leg, and put your left leg in your right pant leg, the zipper will be in behind, and it won't feel right. And I always tell my class, if I ever come into class, my pants are on backwards, someone call for help for me. I'll need it desperately. And if you do the mirror image, it's not superimposable. So those type of things, pants, are, guess what? Chiral. So this one would be chiral. Now, let's do this. Achiral, chiral. And now let's do the mitten with no leather palm. Be careful, this is going to get really funny. See, I'm never going to go to art school. If I have a mitten with no leather palm, and here's this mirror image, and if I rotate this, they'll be superimposable. And therefore, superimposable mirror image without chirality, achiral. And think about it, if you have mittens, or for those of us who have oven gloves, you can put them on either hand when it doesn't have a leather palm. Now, for the piece de resistance, hold on to your chair, people. A car, is it chiral or achiral? Hold on. Here I have a car, there are the wheels. Headlights, steering wheel, brake lights, tailpipe, my 4 doors. And if I did its mirror image, whatever closest to the mirror, I'll see first. My wheels, my doors. Here's the steering wheel on this side. In the mirror image, it will be here, my headlights. And here's my mirror image. And if I pick this up, it's not superimposable. But wait, you say, Dr. White, I can flip this over. Well, if I flip it over so the steering wheels line up, on this one, the tires are pointing down. On this one, the tires are pointing up. And therefore, a car or a truck or a school bus has a non-superimposable mirror image, and therefore it's chiral.
I can tell you're an organic chemist. Your car has an octet rule.
Well, that's general chemistry. What, 2, 4, 6, 8? Actually, with the tailpipe, they're 9 circles. So I just put your observation out of the water. But you're right. Now, do I have time? Oh, I do. Now, I worked for 2 Anglo-Dutch companies, which means I made it to England enough times. Now, one thing, the first time I got to England, luckily I never had to drive for myself. That would have been a headache. Usually I was with a colleague who had a car, or I had a cab I would take, or I took the train a lot. That was fun, because I stayed a lot of times, usually in Manchester or in Littleborough. I also stayed, but mainly Manchester. I was also in London. But first of all, if you look at the car, notice the one I wrote to begin with. Let's call this Roman numeral 1, and its mirror image, Roman numeral 2. Here, the steering wheel's on the opposite side. And the first time this guy picked me up, who was another manager, we're going somewhere. We come to a stop sign, and he stops, and I'm on the drive. Normally would be our driver's side. I put my foot down to use the brake, even though I wasn't driving. He looked at me and started laughing, an American. Now, the other thing that was quite dangerous, seriously, is if you're crossing a street in England, where in America, the cars, when you're coming off the curb, is coming this way. No, in England, it's coming the other way. Twice, I almost got killed. Both times, luckily, a bobby, otherwise known as a policeman, grabbed me by, "What are you doing, sir?" And he said, see the street down there? And they have it printed in major intersections for us dumb Americans. Look the other way. And finally, let me get my collar straight again. I figured out how to safely cross streets in England. How did I do that? I waited until I saw a little old man or woman. And when they crossed, I figured it must be safe. I could walk too. And it worked. Now, let me show you something. This is organic chemistry, and let's talk about chiral molecules. Here I have a molecule, and let's say there was an atom here, silver, black, yellow, red, different atoms. And notice here, I have its mirror image. If I had a mirror right here, red goes to red, yellow to yellow, silver here, and far away black. So these are mirror images. But notice they're not superimposable. If I put this, the red and yellow don't match up, but the silver and black do. Now, if I rotate, didn't realize this is going to be a double show and tell day. But anyways, if I rotate this, now the red and yellow line up, but the black and silver don't. Here's black and silver, black and silver. So these two molecules are mirror images. Hold on. Yep, mirror images, but they're not superimposable, non-superimposable, and these are chiral molecules. And turns out, and I'll teach you later this chapter, your body has a way of distinguishing chiral molecules. And just like putting a key into a lock, if you've got the wrong key, guess what? The lock won't open. And if you have two molecules and your body needs this isomer, these are isomers, and they have another name I'll teach you later on. This might save your life. this might do nothing or kill you. And that's why some of the medicines are very expensive, because you need the right isomer to do the job. The other reason they're expensive is drug companies are greedy. Oops, hold on. My computer just said, I've got to play games on Dr. White. They went pretty long too. All right, everybody see Chiral Center? Thank you. Now, when we talk about molecules, important thing is a chiral center. I'll never ask you what is a chiral center, but you should know that's an atom. And for this class, we're going to talk only about carbon. That's in a molecule that has 4 different groups, otherwise known as tetrahedrally bonded to it. If you notice, the molecule I just showed you is similar to this. The dotted line means it's going back away from you. The wedge is coming towards you. A and D are in the plane of a molecule. If we look at this here, yellow is coming towards you. That would be a wedge. Red is coming away from you. And notice these two are in the same plane like my hand. And that's a way of drawing 3 dimensions. Good news, I won't be doing anything like that in this class, but I just wanted to show you that. Now, we have what's known as a chiral center. And a chiral center has 4 different groups to it, bonded to it. Now let's just do one because we're running out of time. And the question is 3 points each, circle the chiral atoms, or I could have put carbons or carbon atoms. All right, now, quick thing. What is a chiral carbon? It has 4 different groups on it, either atoms or groups. Therefore, if something has 2 or more of the same atom on a carbon, it can't be chiral. So if we look at this, 3 hydrogens, that's out, 2 hydrogens, that's out, 2 hydrogens, that's out, 3 hydrogens, that's out, because it has to have 4 different things. If it has 3 or 2 of the same atom or group on a carbon, it can't be chiral. Now, let's look at this carbon. It has a methyl group a hydrogen, bromine, and this whole long thing I'll call R. And notice this, and this are all different. Therefore, that's a chiral carbon. And I'd circle it, and I did. Now, let's look at this carbon right here. It has a hydrogen hydroxyl group of methyl, and this whole thing here. And these are 1, 2, 3, 4 different things. Therefore, this gets circled. And those are the 2 chiral carbons. And that's what you should know how to do. Now, if I look at the time, we're almost out of time. Boy, time flies when you're having fun with chirality in your hands. Don't forget, my homework assignment to you is take your right hand and hold it up in the mirror and look what you see. You'll see this and prove to yourself your hands are not superimposable. If you really want to live dangerously, try it with your feet, only if you have a full-length mirror. But don't hurt yourself trying to pick your foot up to if you have this higher mirror. Don't. I don't want to get sued. But anyways, important announcement. Next Monday, I will be going through the lipids problem set, fats and oils problem set. Make sure between now and next Monday you do that. And don't forget, tonight at 6 to 7:15, I have my office hour. Please come by, say hello if you have any questions or need any help with anything or anything else I can help you out with. And don't forget, Wednesday is International Chem 170 turn on your webcam day. So make sure you're prepared to turn on your webcam so I can see your real people. Those of you who do, thank you. And with that, I just ran out of time. I'm going to let you out a whole 30 seconds early. Don't tell the dean. With that, I'm going to do my world famous goodbye. Gang gesund, be healthy. Goodbye.